Okay, we're going to start the second session of this morning, and we'll have Bhuvnesh, Jain talking about lensing measurements of Harlow's voice in electrical structure.
Can you guys hear me at the back? Okay. That's pretty good. Okay. All right. So, I'd like to thank the organizers. I don't remember the last time I've been in such a beautiful place. I also don't remember the last time I gave a talk in the first hour of sunshine after 48 hours of clouds and rain. So I'm really feeling the pressure to make this very exciting. The only consolation is that the speaker following me has even more pressure. Sorry, pressure. This is a research talk, so I'm going to show you stuff on lensing that has been done with a few people at Penn, Joseph Clampett, Yudong Fang, and collaborators in the Dark Energy Survey, Eduardo Rosa, Chi Wei Chang, Bhuvnesh, and several others. So, you haven't had like an introduction to lensing, and I know many of you are theorists, so I'm going to give you a very brief introduction to lensing measurements. It's far from being complete. At some other time, maybe there will be lectures teaching, 3 lectures on lensing or something. So, but this is a 3-slide introduction. So, this is a simulation of a more typical, slightly more typical situation, but still exaggerated. If there's a bunch of galaxies at redshift 1 far away, some of them are disk galaxies, some of them are ellipticals, and there's a galaxy cluster sitting right in front of them, then near the cluster you'll get very strong deformations in the tangential direction. Far away from the cluster you'll see smaller deformations. So I want to just mention one realistic challenge in lensing that, far away from the cluster, galaxies have intrinsic shapes, and so you have to measure the lensing shear that's imposed on top of the intrinsic shapes, and you can do that by averaging over many galaxies. If the cluster is spherically symmetric, you can average a whole bunch of shapes and get at the lensing shear. But this is highly exaggerated. In a typical line of sight, this lensing shear is just a 1 to 2% change in the shape of the galaxy. Okay? So you need about 100,000 galaxies even to make a convincing detection of lensing by large-scale structure. And typically, we are now in the era where we use millions of galaxies. So just to stimulate you, without a lot of introduction, I'm showing you a mass map that we made from the Dark Energy Survey. This is work led by Bhuvnesh and Chi Wei Chang, where we used the images of up to 2 million galaxies and then reconstructed the mass distribution that would be shearing these galaxies. So this is a large part of the sky, about 150 square degrees. And the only thing you can see are really gigantic structures. So this, for example, is one of the biggest superclusters known. And the blue shows voids. So red is overdensities, filaments, superclusters, and blue are cosmic voids. And each of them is, 10 to 100 megaparsecs in size. And we also identified the clusters in the same survey that are associated, we think, with the lensing mass. So the circles show clusters of increasing richness or mass, and you can see that where there's a supercluster in the lensing mass, there's a concentration of galaxy clusters. Where there's a void, there's very few clusters. There are some regions that are a little anomalous. So with more data, we'll be looking for things called dark halos, or at least something that's somewhat anomalous in the distribution of mass and light. Okay? So at the level of map making, this is sort of the state of the art. It's the largest contiguous mass map made with a galaxy survey. And so you can see that at the level of maps, we are just about at the point where we can compare mass distribution made without using any knowledge of the lensing material, just using the background galaxies with the actual light distribution. But by using statistics, we can do much more powerful things, including cosmological applications. So we are at an interesting point in galaxy imaging surveys and weak lensing because there are at least three surveys, the Dark Energy Survey, the Subaru HSC Survey, and the KID Survey, that are about to make an order of magnitude advance in data size, okay? From roughly 100 to 1,000 square degrees of detailed lensing analysis. But we don't have results to show you yet. So the results I'll show you at the end are from just some early data. What I'm going to show you instead is, if you like, non-traditional, non-cosmological lensing, where we've tried to go after particular properties of galaxy halos and filaments and voids. So in the next part of the talk, I'll show you what I think are some really interesting new things about the shapes of these things. So to motivate this, there are some very simple sounding questions, which, is there an echo I'm generating, or is that from outside? Okay. Would you like me to be louder or soft? Is this okay? Okay. So there are some very simple questions that for the first time we can answer from the data. You know, we've measured dark matter, we've measured the masses of halos of galaxies and clusters for more than 10 years now, or maybe even 20 years. But how round are these halos? Can we measure the ellipticity of a dark matter halo? Similarly, cosmic voids have been identified for decades, but how truly empty are they? What's the actual mass distribution inside a void? Do these gigantic voids also cluster? And the last question is about halos within halos. Can we identify the mass associated with a galaxy sitting inside a cluster? So these are questions that connect to gravity and properties of dark matter. And we are just starting to make some measurements. So this is not precision cosmology. This is the kind of connection of lensing and some kinds of fundamental physics that's possible even with 10% or 20% measurements. And I'll try to motivate that. Okay, let me start with the traditional way to measure the mass profiles of galaxy halos. It's statistical, where you try to look for this pattern, but instead of, this is a huge cluster. Now, if you are after a typical galaxy, you have to stack at about 100,000 galaxies or 1 million galaxies and measure this tangential shear pattern statistically. So this is something that has been done from the Sloan, from CFH Legacy Survey, from a number of surveys. This is just what we're doing from the Dark Energy Survey. And you can see that this is the tangential shear. So the shear signal here is like 0.1% as a function of angle from the center of a galaxy, so 0.1 arc minutes to 100 arc minutes. So this goes out to like 20 megaparsecs. So the visible size of the galaxy is about here, but we measure the correlated mass associated with the galaxy to tens of megaparsecs. And this is a relatively easy measurement these days to do. You can make this measurement, you can decompose it into a 1 and 2 halo term, and you can also model additional effects in it. Any questions about this? Okay, so to summarize, we can measure the mass profile of a typical galaxy halo, and we can measure the mass associated with it all the way into the linear regime with this one measurement.
Do you find any degeneracy with the anisotropy of the velocity dispersion, or is it
so this is
sensitive?
related to the velocity dispersion. You can measure a mass, at least for an elliptical galaxy, just in the inner parts. So that would be just up to this distance. You could measure velocity dispersion mass, and you can compare them. But yeah, they're just different ways of getting at the same mass distribution. The velocity dispersion is more accurate inside, but then you run out. I'm sorry?
Are you talking about when the halo profile, mass profile, like NFW, or is it 2D map you're talking about?
This is two-dimensional, so the theory curves are projected NFW profiles.
Okay.
Yeah, that's an important point. With lensing, you can pretty much only measure projected quantities, so that's a limitation. Okay. So I claim that was a standard measurement. Now we are after something much harder, which is that from simulations, a galaxy halo looks like this. The inner red part is the visible part of an elliptical galaxy. This is megaparsecs, so 50 kiloparsecs or something. And the shaded part is the dark matter halo. I guess this is for a cluster, that's why it's extending beyond a megaparsec. So I'm going to show you results where we've measured the ellipticity of this dark matter halo. Okay, the previous plot showed you that you can measure the mass distribution, now, average circularly. Now we're going to measure the ellipticity. To measure the ellipticity of a population of galaxies, you have to stack them, and you stack them by using the light. So you say that, let's assume that the total mass and the light are aligned. I'm going to stack a bunch of galaxies along the light, the major axis of the light. And then how do I measure this ellipticity? By way of motivation, let me say that if we can measure it, then standard cold dark matter, produces triaxial halos. They look elliptical in projection, and so it's a consistent story. But some kinds of modified gravities, anything that's related to Mond-like theories, they produce rounder halos on the outside because they don't have this much dark matter. On the other hand, some kinds of dark matter produces rounder halos on the inside. If you have dark matter self-interactions, then in the inner parts of the halo, the interactions isotropize the mass distribution. So there are these fundamental gravity dark matter motivations to look at the shapes of halos, whereas the mass profile of the halos, just spherically averaged, it's pretty hard to disentangle these things. So what does the shear signal of an elliptical halo look like? So first of all, a spherical halo, or the monopole term, looks like this. The shear field is always tangential. Okay. The shear is a spin-2 field, so the one component, this is the positive sign of the one component, this is the negative sign of that same component. and this are the positive and negative of the 2 component. The quadrupole field, the elliptical part of the elliptical contribution to the shear field looks like this. It's just like this, but it rotates twice as fast. Okay, so you had to go 180 degrees to get back to the same shear. Now you only go 90 degrees. Okay, so monopole, quadrupole. For a shear, this is like a cosine 2 theta, this is like a cosine 4 theta. So what we're going to do is we're going to take a measured shear field and separate out the monopole and the quadrupole piece. This is really hard because statistically the signal to noise is 5 to 10 times smaller. And in terms of systematic errors also, it turned out to be a really hard measurement. And so there's a long history of lensing efforts to measure this ellipticity, and there were some tentative detections, but Joseph Clampett, who was then my graduate student, had a very simple and brilliant idea, I think, where he just switched the coordinate system. So I won't have time to describe this, and it's kind of a hardcore lensing measurement thing, but the point is that everybody did measurements in a coordinate system that rotated, so that this shear was always along the x-axis. So people used to rotate the coordinate system so that they always got the shear in just one component, which makes sense for the monopole. But for the quadrupole, it turned out that when you're trying to disentangle systematic errors, spurious shapes induced due to the telescope and atmosphere, then there's a better coordinate system is just a fixed Cartesian coordinate system. So that's the 2-minute version of his insight. And so we just took Sloan data, which has been around for nearly a decade, and switched coordinate systems. And so just to show you what the measurements look like, this is this particular component of the shear, and the blue points. So these are, okay, let's just look at the upper 2 panels, where the blue points are the lensing signal. The red points are a test that we can do that should be consistent with 0. And so this doesn't look like an amazing measurement, right? But this is a field where just getting a detection is a big deal. So you can see that compared to a prediction with almost no free parameters, the measurement shows an elliptical contribution, a quadrupole contribution from 0.2 to about 2 megaparsecs. And just looking at the error bars, which are correlated, you would not be surprised to hear that this is a 4 or 5 sigma detection.
Question. What's on the y-axis?
The y-axis is the projected mass in certain units contributed by the quadrupole term. It's sort of not a particularly intuitive quantity, that's why I didn't go into it. So with those kind of measurements, we can then fit for the ellipticity of these cluster halos. And this is the kind of new and convincing thing about a measurement, that we could make an estimate using a component that is immune to systematic errors. And that's the dashed curve, whereas the black line is a more aggressive way to do it, which involves modeling systematic errors. So anyway, from the measurement point of view, we think this is a big advance. And so we can estimate the axis ratio of projected galaxy clusters. And the big caveat to interpreting this is that the mass and light can be somewhat misaligned. So we only measure the contribution that remains after you account for misalignment. So the true axis ratio is probably something more like here. Okay, so for galaxy clusters, then, sorry, go ahead. Right. So now we can do a lot of studies on mass and light. So in the two methods, in this method we used only the central galaxy, the brightest cluster galaxy, to align the mass distribution, to align the clusters. Whereas on the left we used all the satellite members of the cluster. I'll show that in the next slide. So these are the contours of, if you stack a few 10,000 clusters, then this is the contours of the satellite distribution out to half a megaparsec. And we find the mass distribution is pretty consistent with this level of ellipticity. And then we could compare this method to using the central galaxy of the cluster to align the mass distribution. Okay. So I mentioned that mass and light may not be aligned. So in lensing and cosmology, a big question is, how aligned are they? Because if they are extremely tightly aligned, then in weak lensing cosmology, there's this problem of intrinsic alignments. And so this has been studied quite a lot from simulations, including by people in this room. And so now we are trying to do this from measurements. And so this is not part of our published work yet, where, well, this one is. So now we're talking about galaxies. So these are luminous red galaxies, where we make a pretty significant detection of halo ellipticity. Sorry, I switched from axis ratio to halo ellipticity here. So this is like an axis ratio of 0.75. Then we studied spiral blue and elliptical red galaxies. And we find that they are very weakly aligned, mass and light. But to the extent that there is some alignment, ellipticals show some alignment, spirals show some anti-alignment of mass and light. Okay. This was I thought, a surprising result. Then I went back and looked at the literature. And so, for example, there's this paper by a group at CMU, including Tiziana. And they have studied the positive and negative alignment of disk galaxies, and there's other work that classifies disk galaxies depending on when they're active accretors or not, and they can be positive or negatively aligned. So we are really excited about both learning about this galaxy formation literature and being able to provide an empirical, the first kind of empirical check of whether spirals are positively or negatively aligned.
For these elliptical and spirals, then which redshift are they?
So,
it's Sloan, so it probably is small, but...
So this is Sloan, Sloan imaging survey. So the mean redshift is of these lenses is like 0.2 or so.
Because
and we are not able to test for redshift dependence. But of course, one reason we are doing these measurements is to then apply them to dark energy survey data. And then with higher signal to noise and a deeper redshift coverage, we should be able to study redshift dependence, at least in 2 or 3 bins.
And the Sloan 3 doesn't allow you to go up in redshift for at least for the massive ellipticals?
Sloan 3, you'll have
yes,
to remind
to
me.
go to 0.5 or to...
Which is Sloan 3?
So
Voss?
Yes.
Oh,
Voss,
okay.
yeah.
No, but we need background imaging to do the lensing. So,
Okay.
yeah. So we can't really do better than this LRG sample. So the LRGs go to 0.4, 0.5. Yeah. Yeah, so the LRG result goes up there, but we didn't try to look for redshift dependence because we're just getting a detection. Yeah. So yeah, so these are very interesting next steps. Okay. So I'll take just a few minutes to show you one other new thing, which is related to these subhalos. So you measure a mass profile of a galaxy or a galaxy cluster, and you can look for a small feature due to subhalos within that profile. And that feature, so if you then center on a satellite galaxy, then the profile looks like this. You see a bump due to the central galaxy. So we are now implementing a trick to try to isolate the mass distribution of satellite galaxies themselves. So what we do is we center on a satellite galaxy, measure the mass profile, but it's completely dominated by the host galaxy. So then we take that satellite galaxy mass profile, and from it we subtract the profile measured around the opposite point. And when you average over a whole bunch of systems, the opposite point is just like a random sample of the host halo distribution. So when you subtract them, you get a profile associated with the satellite itself. There's some detailed modeling and iteration you have to do to handle this negative dip. But so this is unpublished work, but we hope soon to have this measurement of kind of a model-independent measurement of satellite mass profiles. Okay. I'm now going to switch and talk about voids for 10 minutes. So this is the red galaxy distribution in Sloan projected on the sky. And the green circles are voids identified according to some void finding algorithm. Okay? So the field of studying voids in the galaxy distribution is a pretty mature field. Our contribution was to measure the lensing due to these voids. So voids have like a negative mass distribution for all practical purposes in cosmology. Okay? So let's go back to this. So, there's a mean density of, of mass distribution. And so anywhere where there's a deficit of mass, it's like gravity is repulsive. Because things will move away from the center of a void, after subtracting out Hubble flow. They'll move away, and they'll move towards these concentrations of matter. So when you look at the mass distribution and the lensing, then light rays, an overdensity will cause converging light rays, and underdensity will cause diverging light rays. So in the math, you can just replace the mass the mass term by a negative sign. Our paper got some attention of some journalists, and I had to spend an hour on the phone saying, dealing with this repulsive gravity thing and making sure they don't say something that sounds crazy. But in the math, it's pretty easy. The other really non-intuitive thing in the lensing is that, a halo mass distribution is very cuspy. And so the lensing signal keeps rising towards the center. And so everybody's used to seeing that and thinking that, yes, the density is higher, so the lensing is higher. But actually, lensing is sensitive to derivatives of the density profile. So when you look at a void mass profile, shown here, then this is cosmic mean density. This is the fractional difference from the cosmic mean. So this would be completely empty. So this is minus 0.6, say. But the density profile in the inner part of the void is very flat. So lensing is quite weak in the inner part of the void. And it peaks. So the lensing prediction for this profile is this curve. And it peaks at actually close to this distance, which is the size of a void, in this case, a 25 megaparsec void. Okay? So this is a measurement of a stack of order 10,000 voids of 25 megaparsecs radius, and the black is the negative mass distribution inferred by the shear of the void. So in shear terms, the void produces a radial shear distortion rather than a tangential. And the magenta is this test of the B mode, which we expect to be consistent with 0. So this is in units of the void radius. The void radius ranges from 15 to 30, so it goes out to at most 90 megaparsecs. Okay, so we get a pretty comfortable signal at 70, 80 megaparsecs from the center of a void. You know, this signal is 10 to the minus 4. Okay, so imagine a galaxy. Its shape is elongated into an ellipse with axis ratios 1 to 0.999. So statistically, we are able to measure these really tiny signals. So you can see that
Probably it's my eyes don't seeing, but I see a lot of. Would you think it's a good fit to the black? No, I don't know. I mean,
yeah,
you have 2 points design in the deep, but then you have a lot of scatters above. Or what's that?
Yep. You know, there's some correlation between the error bars. So these 3 points are all deviating one way, but that's not a 3 sigma deviation. That's like a 1.5. No, the magenta points are a test of this so-called B mode contribution.
Yeah.
So we decompose the shear into an E and B mode. So if you look at the formal goodness of fit of the black points to this curve, it's actually very good.
It's very good.
Yeah.
Okay, so it's misleading because you see those black points close to the magenta point.
Right here.
There, that's right.
That's right.
That's a bit. Yeah.
You do? Yep. Yep. You see, you have 3 points that are more than a 1 sigma deviation. And you expect maybe 2. But yeah, the main point is the error bars of neighboring bins are correlated. So these 2 and these 3 are not as significant as they appear to the eye. So, you know, so that's like a 7-8 sigma measurement, I think. And even looking 5 years ahead, it's not going to be much better than a 10 sigma measurement. Whereas with galaxy-galaxy lensing, we're going to get to 100 sigma, you know, with data we already have from DES. So what's the point of making these measurements? I mean, voids are really cool things. But it turns out that for particular tests, like gravity theories, you know, we discussed this yesterday, that there's this idea of screening, that because we have general relativity in our galaxy, it's very likely that inside halos of galaxies and clusters, you get very close to general relativity. Whereas in the outer parts of the universe, where the density is low, or the potential is low, or the acceleration is low, depending on the theory, you can get significant deviations. So, so this was a theory paper that was motivated partly by a measurement, where they looked at these Galilean models that are kind of related to massive gravity, and looked at the prediction. So you want to compare red with blue. So red is GR, and blue is this particular model. And you can see there's like a factor of 2 difference in the prediction, easily. Right? Inside halos, these 2 models would agree to better than 10%. So just in one plot, this is a point, and a really important point about testing these gravity theories, that you're modifying gravity to get rid of dark energy, right? So dark energy dominates the energy density of the universe. So somewhere in the universe, it's like an order unity change you're doing, very roughly speaking. So this is one place in the universe where, in terms of the gravitational field, you get an order of unity deviation. So there's still some issue. These guys had to do some approximations to generate these predictions, and Austin and others have looked at the validity of this approximation. And so in the inner parts, it's not conclusive that this calculation is entirely justified. But this qualitative steepening of the void is valid. So we actually have to do a lot more work to connect this prediction to our theory, because you have to also make a mock catalog of the galaxies used to identify the void. So it's a lot of work to connect these gravity theories to data, because you have to simulate them if you want to go after these nonlinear regime signatures. But it's well worth it because of this qualitative point that you can get big signatures. So I would have, someday loved to give you a modified gravity talk, but today I won't. What I will do is point out that, as you heard from Claudia and Eric's excellent talks, that there's signatures on very large scales, but also signatures in stars, galaxies, and I'm adding voids, halos, and filaments. Please talk to Austin Joyce, who's an expert in all aspects of the theory of this. Don't ask him a lot about galaxies, okay? He can identify a galaxy, but he prefers to do the calculations. This is our review article where we describe both the theory and both the large scale and the screening regime signature of these gravity theories. So just since you heard about BAO and stuff, I can't resist showing one plot of void clustering, which has been, again, studied from mock catalogs, but from data, this is the first measurement that we put out a few months ago. So this is the void profile on a, inside the void. So this is the galaxy distribution. The void gets, This is the void galaxy cross correlation, okay? On the y-axis, distance on the x-axis. This is the zoom in on the inner part. So this is a void of about 20 megaparsecs. Inside, it's nearly empty of galaxies. Outside, there's a little compensation region. The green and black are data and mocks. So this is the part that's new, where we measured the large-scale correlation out to 200 megaparsecs of voids and galaxies. This is the BAO bump. And this is the part that I really wanted to show as being quite new, the void-void correlation. So that's a really difficult thing because there's not that many voids. We're also doing these void studies in DES. So this is one paper that's out. And but we are going to be working with a lot more data by this summer. So I won't say more about it. Okay, sorry, I'm going through a few different topics. So now I'm going to come to cosmology and lensing with DES. DES is the Dark Energy Survey. So I don't need to give you much of an introduction, but I'll just mention that cosmology probes, as Eric Linder emphasized, can be split into probes of geometry and growth, and they tell us different things. And the second point that's worth emphasizing is that combining the CMB with the late-time universe gives us this huge lever arm in both time and length scale. So I'm just going to give you a brief intro to DES lensing here. So this is one plot. There's several papers that have looked at the CMB versus the low redshift universe. This is sigma 8, the amplitude of mass fluctuations, and omega matter. This is Planck. This is a year old, so there's some updates to this, but the qualitative story is mostly the same. That you look at the CMB, translated to redshift 0 using lambda CDM, and then you take direct measurements of the low redshift universe, and they seem to prefer lower values of the amplitude of mass fluctuations. So Eric showed the similar story and pointed out that the simple scalar tensor gravity theories would have predicted these things to be higher. So we have a possible puzzle on our hands, but there's a lot of subtleties to be discussed. So that was a plot from a year and a bit ago. Now we have data from this dark energy survey. This is the camera. This is the telescope in Chile. And Tommaso Gianantonio is going to give you a talk on Friday showing some other results from DES. So this is the footprint of DES. We've completed more than 2,000 square degrees to a certain depth. But the results that we have right now are from, embarrassingly old data, but that's life. Data analysis takes a long time. So I'll show you those results. The Cosmology program involves a joint analysis of galaxy clustering, weak lensing, and galaxy clusters, and also type 1a supernovae, both from DES and outside. So let's pause to think about how we do cosmology with weak lensing. I've shown you how lensing gives you the mass profiles of halos and voids, but you can also do a direct measurement in which you don't identify halos or voids, but just look at all the mass distribution there is in random directions in the sky. So to do that, this is a simulated shear field. And so this would be a big galaxy cluster, but in general you have filaments and voids, and you don't want to always identify where the clusters are. You just want to get all the correlations of the mass distribution. You can see this field has coherence on all scales that you can see. So what we do is take the shear at this position, the shear at this position, shown exaggeratedly here, and take like the dot product of the two shears. It's actually a complex or spin 2 field, so it's like this shear times the complex conjugate of this shear. So that 2-point function is a measure of the projected 2-point function of the mass distribution. In other words, the power spectrum of the mass distribution. And I already showed you that we can also measure the cross correlations, and so that we can also measure 3-point functions and peak statistics that some of you have studied. So one can make these partially redundant measurements and do interesting tests and cosmology with them. So this is our measurement of the shear 2-point function, along with the prediction of a lambda CDM cosmology. These are two different shear measurement methods. This is the second 2-point function because it's a 2-component field. But let's leave all these details aside. So this is a state-of-the-art measurement of the lensing 2-point function on the smaller scales of a few arc minutes, which is about 1 megaparsec. The shear is still less than 1%, so the square is less than 10 to the minus 4. On the larger scales, it goes down to 10 to the minus 6. So this is about 10 megaparsecs. So the right half of this plot is linear regime. The left half is quasi-linear regime. Okay? So this is something you can compare to a direct prediction of a mass power spectrum. And you can compare to different cosmological models and learn about dark energy and so on. Let me just skip this actually. So the other state-of-the-art thing is that you can split your galaxy sample into different redshift bins, and you can do what's called tomography. So this is 3 redshift bins, and the auto and cross correlations of the 3 redshift bins. You can see that our signal to noise is not that good with this early pre-survey data, but you can see a general trend that as you look at more distant galaxies, the shear signal gets bigger, and the spacing of these different curves tells you something about dark energy, especially when you compare it to the CMB. So you have a CMB normalization, and then you can make predictions at different redshifts, and that tells you about omega dark energy and the equation of state. The shape of the curve tells you about other things, like the shape of the primordial power spectrum, massive neutrinos. So there's like a full cosmology program you can do. This is just kind of a visual thing that you can convert all those measurements into a 3D mass power spectrum with some modest assumptions. And so this is P of K versus K. And the nice thing is you can plot the lensing measurements and CMB from Planck on a single plot. And you can see why lambda CDM is a very successful model, because you can take a redshift 1100 measurement and a redshift 0.5 measurement, and by eye they lie on exactly the same curve. And you can also plot other things, galaxy surveys, Lyman alpha, and so on the same plot. Here? Yeah, I didn't explain this. The black is the thing I wanted to show. The colored points are just each bin one at a time. So for our own purposes, we wanted to see how the different bins contribute. And the magenta is the CFH legacy survey. So, so yeah, I can make one point here that the CFH legacy team found that sigma 8 was a little lower than Planck. In our analysis, we find that it's pretty consistent with Planck. Right, good point. Right now, the errors are such, as I'll show you, that there's not a lot we can say. So this is DES, and this is Planck, assuming lambda CDM. Planck doesn't tell you much about sigma 8, as much about sigma 8 if you drop the lambda CDM prediction. So the only point I want to make is that we are seeing higher amplitudes than CFH legacy survey and some other measurements. But you can see that we have a ways to go before we can do an interesting comparison with Planck. So this is another study where you can combine galaxy clustering with galaxy-galaxy lensing. So this is what's called W of theta galaxy clustering. This is the lensing of those same galaxies. And I won't dwell on this, but I'll just show you that this is something we hope to put out in a few weeks. That now this is WCDM, so if you allow dark energy to be free, then this is the Planck contour using a certain set of Planck data. This is this galaxy clustering, galaxy-galaxy lensing, and this is the previous shear-shear correlations. So this is again with the SV data. We have 10 times as much data already taken. So if you imagine a square root of 10 improvement in the DES contours, you can see that this game will become very interesting, hopefully by this summer. But this is mainly just to show you the sorts of things one can do. This is an advertisement for Tommaso Gianantonio's talk on Friday, where he'll show you a number of interesting things we can do by combining DES galaxies with CMB measurements of the same part of the sky from SPT. Okay. So just to wrap up, so we have about 10 times as much data taken that is being processed right now, and we hope to have the first paper actually will be hopefully out in a few weeks, but a full cosmology analysis maybe this summer. So that would involve various subsets, but also a full joint analysis of all two-point correlations, and various things one can do by combining galaxies and the CMB. So thank you.
Questions? If there are no questions, then we thank the speaker again.